Hey guys, Mr. Riz here to help you out with the 1-1 in Algebra 2. Here we go. So these are video notes. All right, so let's get this started. All right, so this first one in 1-1, we're talking about functions and continuity. Okay, so we got a little bit of warm up here. So Anita is making chicken noodle soup. The recipe calls for 3 times as much broth as meat. All right, so what we want to do here is complete this mapping situation here. And then we're going to end up writing a function where x is the number of cups of meat and y is the number of cups of broth. So remember here, like back in Algebra 1, that the domain is your x and your range is your y. And so in this case, the x is going to be the number of cups of meat, and then the range would be the number of cups of broth. So go ahead, take a second to think about, okay, what would that mean? So 1 cup of meat, if it's got to be 3 times, would be 3 in the range. 2 would go to 6, 3 would go to 9, and 4 would go to 12. Okay, you can see that. And then to write that as an equation, we would say y, the number of cups of broth, would equal 3x. It would just continue to go like that. Okay, we got a couple more here just to kind of warm up. So we're going to make a function for each situation here and then describe or map that it describes. So first one here, we got for every dollar a customer spends, Mike earns a 15-cent tip. Okay. Let X be the number of dollars a customer spends. We got Florida has a sales tax of 6%. If an item costs $5, you must pay $5.30. If an item costs $10, you must pay $10.60, and so on. Let X represent the price of an item. And then here, we have the domain with 2, 3, 2, 0, 3, and -3 in the range. So you plugged in 2, it's going to give you a y of 0. Plug in 0, you're going to get a 4. If you plug in 3, you get -5. If you plug in -3, you also get -5. So take a second. We got A, B, C. Try to match these up. Pause if you need to. All right, and here should be the answer. So the first one here should be B. So we got f of x equals 0.15x. A couple dead giveaways. The 0.15 tip. You're going to have 0.15 in the function. Next one here, we have 6%. So 6%, remember, as a decimal is 0.06. You move that over 2 spots. And then the reason why it's 1 is because we're playing 100%, 106% of the item. So one thing you can always check, plug it in. 5 times 1.06 is 5.30. Same thing with 10. 10 times 1.06 is 1060. And then A, the reason why we can have a domain go to 2 values is when we square. If you square a +3 or a -3, you get 9. Put the negative sign on our side. Both of those would be -9 plus 4 is -5. Okay, so these are going to be the standards that we covered in this section here. So you can read through those if you'd like. Disregard. Big thing is our goals here. One is to determine whether functions are one-to-one or onto. Next thing we're going to look at is determining the continuity, domain, and range of functions. And the third thing is to write the domain and range of functions using set builder or interval notations. Okay, so here's some vocab for you. A function describes a relationship between input and output values. The domain is the set of x values to be evaluated by a function. The codomain is the set of all the y values that could possibly result from the evaluation of the function. The codomain of a function is assumed to be all real numbers unless it's otherwise stated. The range is the set of y values that actually result from the evaluation of the function. Okay, so the range is contained within the codomain. Okay, so pretty much this class, codomain is pretty much always going to be all real numbers. It's like, okay, yeah, I guess anything could be possible. The range is going to be what actually exists. They're kind of confusing, the two. All right. If each element of a function's range is paired with exactly one element of the domain. So one element of the range, the y's, is paired up with the one element of the x's, and only one. All right, that is considered to be one-to-one. If a function's codomain is the same as its range, then the function is an onto function. Okay, so pretty much if the range is all real numbers, it's going to be onto. Okay, so we're going to look at these here and determine the domain, the range, and the codomain. So if you kind of look at domain, is going to be, hey, everything from the left to right. This graph, imagine if we could go here, we'd be going all the way to the left, all the way to the right. So the domain is our x, left and right. Your range is the up and down of the graph. So codomain is up and down all the way across. Range is, okay, going to the graph. So this graph stops here. Okay. So if we were looking at this, we would say that there are no restrictions on the domain, and the domain is, and remember, this is where you guys will fill in your blanks in your notes, is all real numbers because it goes all the way to the left and all the way to the right. All right. The range, there's a maximum here at 0, a y value of 0. Remember, you're only looking at the y here. So the range is the y is less than or equal to 0. And here we go. Because it's not stated otherwise, the codomain, we're looking all the way across, is all real numbers. Okay, so now what we're going to do is go back and look at that to determine whether the function is onto. So the range is not the same as the codomain. Remember, the range was less than or equal to 0. The codomain was all real numbers. So it does not include the positive numbers that we were looking at. Therefore, the function is not onto. Okay, so next look at this one here. Pause this, give it a try here. What is the codomain of f of x? For what codomain of f of x is it an onto function? So look at this here. Take a second pause. Okay, should be A. So the codomain would have to be stated as just y is less than or equal to 3 for this to be an onto function. Okay, so with codomains, you could specify a specific area to look at. Typically, though, codomain, you're going to be looking at all real numbers, though. So that would have to be stated that to be a onto. Okay, next, let's take a look at this function here. So we got a graph. Each year, we have the number of gold medals, the number of silver, and bronze. Okay, and we might have to go back and forth to this graph. You guys have it in your notebook. Okay. So we're going to analyze the function here and determine whether the domain and range of each function and state whether it's onto, one-to-one, onto, both, or neither. Okay, so if we look back at the gold medals, and if you guys go back to the chart there, so we can say like, hey, a function here, f of x, gives the particular number of gold medals won in that year. All right, the domain is the column year, so that would be our x, and the range is the number of gold medals. So domain is years, y is the number of gold medals. All right, the function is not one-to-one because 46 is paired with two values. Okay, if we look at the domain, it's both with 2016 and 2012. Okay, so it is not one-to-one because that range number, the y number, appears in two different x spots. And 36 is in the range paired with 2 twice. So you got two of them that repeat. It's not good. So the function is not on because the range does not include every whole number. So that's the one thing to look at too. The range didn't have every single number between 0 and infinity, so it doesn't work. All right, so if we look at silver medals here, in that particular year, it's kind of same thing. The domain would be the years. The range would be the number of silver medals. Now, with silver medals, the function is one-to-one because there were no two values that were shared from the domain. Okay, so the range had all unique values. Okay, and that was shared in every single value of the range. All right, the function again is not onto because it doesn't include every whole number. Okay, so that was with the story problem. Now let's look at the graph here. So if we're looking at just strictly graphs, okay, we're going to determine whether it is onto, one-to-one, both, or neither. So we got f of x, g of x, and h of x. Okay, so we got f of x here. Okay, this graph indicates that the domain is all real numbers. It would go all the way to the left, all the way to the right. And the range is all positive numbers. It never goes below 0. Okay, so every y value is paired with exactly one unique x value. You can see there's never a time where our y values are the same. Like if we did a horizontal line, we'd never touch it twice. I mean, technically here it'd be close, but it's not. So the function is 1-to-1. If the codomain is all real numbers, then the range is not equal to the codomain. Okay. So the function is not onto. Okay. Next, let's look at this graph here. All right. The domain would be all real numbers because this goes all the way to the left, all the way to the right. Eventually it will get there. All right. And the range is y is less than or equal to 4. It looks like we start here at 4 and we go down. Okay. So each y value is not paired with a unique x. If you can see here, like we got a y value of 0 here, -1, and another y value here at +3. You can say same thing down here. We have multiple times where we repeat the y values. So the function is not 1-to-1. The codomain and the range are equal. No, they're not. So no, I guess the codomain. Okay. No, that should be is not onto. Okay. We'll look at that. Don't worry about that one. That one, did I say is not? I need to go. No, it'd be fine. That one should is not onto. All right. So this graph here, we're looking at the domain and range. The domain is all real numbers because that would go all the way to the left and all the way to the right. The range is all real numbers because it goes all the way down and all the way up. Each y value is paired up with exactly one x value. So it is 1-to-1. And the codomain, all real numbers, is the same as the range, all real numbers. So it is onto. Okay. Last thing we're going to talk about here is continuous functions, discrete and continuous functions. So functions can be one of three things. They can be discrete, they can be continuous, or neither. All right, real world situations where only some numbers are reasonable are modeled by discrete functions. Okay, something that typically you would have, like you wouldn't be using decimals for or anything like that. Okay, so these situations where all real numbers are reasonable are modeled by continuous functions. So something that you could have real world numbers where you could have decimals or everything in between, those would be continuous functions. So a continuous function is graphed with a line or an unbroken curve. Okay. A function is not continuous or has a discontinuous function if there is a break in it. Okay, a discrete function is a discontinuous function, so there's breaks in it, but are connected by points. Okay, so you can kind of see like point values going through. So a function that is neither discrete nor continuous may have a graph where some points are connected, but other points are not. Let's see what those look like here. Okay, so we're going to determine whether these functions are discrete, continuous, or neither. All right, and then if they are, we're going to look at the domain and range. Okay, so if we look at this first one here, this f of x function, this function is continuous. Okay, this does not break any of the gaps in this. This is a solid line all the way through. The domain would be all real numbers because it goes all the way to the left, all the way to the right. Range is all real numbers because it goes all the way down and all the way up. All right, this function here, this function is neither, okay? It does make a nice straight line, but there is a break right here at the point 2, 1, okay? Because that, we can technically say the domain does not have a 2 value, and we can also say the range does not have a 1 value, okay? It's missing those. Other than that, there's parts that are straight, but there's a gap, so that is neither. That is a discontinuous graph. All right, now this function is made up of a bunch of points here, totally different. This function is discrete, and it's just because it's made of distinct points, okay? So the domain would be the x numbers, -3, -2, -1, +1, +3, +4. And the range are the y numbers. So if we start down on -3, -2, 1, 2, 3, and 4. Okay, so if we think about here, you know, does the range of a function really need real numbers to be continuous? Think about it, pause the video. Does the range of a function need to be all real numbers for a function to be continuous? No, as long as there's neither domain or range has. So you think about like a parabola. A parabola is a nice smooth curve, okay? All right, it works. It is a function, but it doesn't have a range that's, you know, like less than 0 or anything like that. Okay, let's look at this one here. and try to determine whether this one is discrete, continuous, or neither. So we got a price. So if we're at a coffee shop, we're buying, bulk coffee here. If I want to pick a bag, fill it up myself, up to 2 pounds would be $8 per pound. All right, and then they sell other bags that are pre-filled for 2.5 pounds for 20, 3 for 22, 5 for 35. Okay, and then what we're going to do is state the domain and range of that. Think about it, try it. Let's check. All right, because the customers can purchase basically any amount up to 2 pounds, the function is continuous over the points 0 and 2. Okay, so that means they could buy 0.1 pounds, they can buy 1.375 pounds, they can buy any number between 0 and 2. Technically, they could buy 0 pounds. It'd be kind of weird, but they could work. Okay, but for the larger quantities, the coffee is sold in distinct amounts. So that function is discrete. Okay, since the domain and range are made up of neither signal intervals nor individual points, the function is neither discrete nor continuous. So it's neither. Okay, because if we would look at the graph would kind of curve up, and then after that have some dots. Okay, so the domain of the function would be between 0 and 2, and then x equals to 2.5, 3, and 5. Okay. This function, this represents the possible weights of the coffee beans that the person could purchase. So that's what domain is. All right, the range would be from 0 to 16 pounds. Okay, buying 2 pounds would be 16, and you could buy any number in between. And then after that, you're only spending $20, $22, or $35. So this represents the possible cost of the beans. Okay. Last thing we got to talk about here is set builder notation here. So when we're looking at the domain and range, there's a couple ways that we can represent those as like expressions. And so we can consider the values of this graph here. So the values of this graph would be any number less than 2, not including 2. So what we can do before an algebraic way is to write this in algebraic notation. And to honestly, this is what you guys are probably used to. You'd say x is less than 2, not less than or equal to. X is less than 2. Excuse me for a second. Hopefully that's better. All right. Set builder notation is very similar to algebraic notation, except for you use this like vertical brace. Okay. And then there could be the sigma symbol here. Okay. That is read as an element. So it says like for every x such that, and this is pretty much what you would say here, for every x such that x is less than 2. Okay, so very similar to algebraic notation, you would just have this bar here. Now, interval notation uses parentheses or a bracket. So a parenthesis would be something that it doesn't include, doesn't like finally reach. A bracket would be a hard point. So this would be like your less than or greater than signs. These would be your less than or equal to, greater than or equal to. So this one, it would be less than, or not less than, it would be from negative infinity to 2. Now, one thing, you could never touch negative infinity, so that's why it's a soft bracket. All right, so now what we're going to do is try to challenge yourself. Let's write this in set builder notation and interval notation here. So we got this graph here, the domain, what would it look like? All the way to the left, all the way to the right, and the range all the way down and all the way up. Give it a second, try, let's check. All right, so the domain would be all real numbers. So the way that we would write it in set builder notation is x such that x is the elements of all real numbers. Okay, so you kind of use that fancy looking R here that's on there. The domain in interval notation would be from negative infinity to positive infinity. So we'd put those infinities in brackets, nice soft ones. Now the range here, we'd have to look. The lowest that the range goes is down to -6. So it's from -6 and up. So the way that we would write the range in set builder notation is y such that y is greater than or equal to -6. So it goes all the way down to -6, touches it, and goes back up. The way that we would write that in interval notation is we'd use a bracket -6 to infinity. So we do touch the point -6, so we are going to put that in a hard bracket, and we're going to go all the way up to infinity. All right, so let's try this on your own. Write the domain and range of each function in set builder and interval notation. So pause this video, give it a try. Let's check your work. All right, so this one here, the domain should be all real numbers. It goes all the way to the left, all the way to the right. So you can see here, you got x such that x is an element of all real numbers. The domain in interval notation would be from negative infinity to positive infinity. Now the range goes all the way up to 3 and down. So we'd have y such that y is less than or equal to 3. The way that we write that in interval notation is from negative infinity to 3. We look at the straight line, the domain and range is all real numbers. So you write it out just like how we did over here for the domain. The range is the same as the domain, except for you're putting y's here. I kind of prefer interval notation. I'm never going to have you guys do one or the other. Like, say, I just want you guys to be comfortable with both of those. And then if you have a preference, you can do either one on the test. All right, try this one here. We have a neither function here. Well, how would we write this in domain and range? So the domain would be from all the way from negative infinity to negative 1. So everything less than negative 1. Notice that here, soft bracket, and then greater than or equal to 0. So the domain would be x such that x is less than negative 1 or x is greater than or equal to 0. Now, the way that we write that in interval notations, we'd have to use this union symbol here. So we're going from negative infinity to negative 1. Notice the soft bracket there, parentheses, and, or union, hard bracket 0 to infinity. Now that you got that, if you need to go back, change your range. Let's see if we can do it again. All right, the range going from down to up, we got from everything less than negative 1. That's where the y is. Or everything greater than or equal to 2. Okay, so interval notations from negative infinity to negative 1, soft bracket, because we don't actually get to touch negative 1. But then hard bracket here, because we do start at 2, and then we keep going all the way up. All right, now that you got that, give this one a try. Hopefully that kind of cleared some things up. Should be one of the last things we check. All right, the domain should be from x such that x is less than negative 1, or x is greater than or equal to positive 1. Hey, Wyatt. All right, you can see what it would look like in interval notation. The range is actually all real numbers because we go all the way down up to here, but then we come back. So we do cover every single point. Even though there's a hole here, it does get covered. Okay, so we got some exit tickets here. You guys can try these ones on your own. But the big thing that I want to make sure you guys do is you guys do your work on your CYUs. If you guys have any questions here, let me know. But thank you again for watching. You guys have a great rest of your day.